So you've started the recording.
I'm going to start. Yep, I've started it. So hang on.
All
And
right, I see that. And accompanying me is Chris Cunningham. Are you going to display the poster, Lisa? Or should
I
I?
am. Yep, I am. I'm going to get it up here
All
for
right.
for
I'm
you.
thrilled to go first. I'm not starting my 3 minutes ago.
Well, it looks like you're going to be talking the first and second here, huh?
Yeah, 2 different posters and 2 different partners.
Yes. Okay. Hang on. Let me get to the next page here.
Great. That's there. And Chris, turn on your mic too. I'll start and Chris will end. So I'll try to do about 1.5 minutes. Our other partner, Danielle Colbert Lewis, a librarian who's done a lot to set up things for us, is not here. Open education resources are vital to what we're trying to do with spreading information and making it open for people to use. So we've worked hard as part of a pilot training and a grant with the Institute of Museum and Library Services to provide open education resources. We've set them up at the NC Docs site, which is part of UNC Greensboro, and we're covering all sorts of materials that were used in December 2021 and 2022 January. Folks like Jerry Perry, who I see is in the audience, were one of our speakers, and we've tried to provide to anyone now that kind of information that they can use. So we want it to be open. That means it is open now at this time, and we hope that everyone in the community of practice in healthcare research, both librarians and researchers, we work with clinical researchers in health informatics. And I'm going to turn it over to Chris, who works very hard with our librarians here at the School of Library and Information Science. Go ahead, Chris, and finish the 3 minutes.
Thank you, Deborah. So yeah, the idea behind it was to not only expose from our end, looking at library and information science professionals, as we are often usually the curators of accessibility and archiving and so forth, but also to really be able to bridge that gap between kind of information professionals and healthcare professionals and really opening that up. And so we had a phenomenal blend of students come in looking at that. We had professionals from the MCBK crew as well as health informatics from the LIS world. And then the idea behind it was to use those as kind of a starting cohort, but doing so in such a way as we develop much more longer term useful resources. And so the focus right out of the gate was always to develop something that was going to be open educational resource so that we could then use it on down the line. One of the big challenges really was just to find a repository, because those are unfortunately far and few between. But the idea is to lean into both practitioners within the healthcare profession as well as information profession, put those two pieces together, and then put together the results out there so that people could then stand on our shoulders and be able to expand upon what we got started.
Yes, and I hope people will follow the link and find it. They can email me or Chris. And some of the comments from the attendees included, hey, we want to strengthen partnerships with the National Library of Medicine and update MCBK. We want to expand and integrate algorithmic justice, which was an important subject that we had. But that gives me a chance to segue, Chris, into my next poster. Is that all right? Please go ahead, Lisa, and thank you, Chris. Put up the next poster, and joining me will be Amrit Vestrella.
Okay.
And I just want to make sure, Amrit, that you've got your microphone working. Are you there? I know you were there earlier. So he and I have been working and building on an effort that I started with one of the groups, one of our work groups, which is sustainability and there we go. Sustainability and inclusion was the work group we started with. So I'm waiting to hear. Are you there, Amrit?
Hello. Yes, I'm here.
Great. So I will just start and leave you most of the time. As I was explaining, okay, I'm starting at 3:25, 3 minutes by what's on my clock here. Thank you, Lisa. Bias in AI and machine learning refers to when there's systematic errors in the data, the algorithms, or the models that lead to discrimination and unreliable outcome. We've worked real hard, and I know I started with the, as I mentioned, the work group that included Jerry Perry and Terry Wheeler, and we've done a lot. And now Josh Rubin is heading us up as HEAL. But we really are not finished. As my helper, Amrit has been with me again this year, and we've added more to our original literary review and are having new findings. So you go ahead, your turn, Amrit. Amrit Vestrella from North Carolina Central University.
Hello, good afternoon. So the research that we found was within the past 3 years, making it really relevant towards AI and the bias in AI currently in the healthcare field. And I just want to get straight into the findings of our review. The first findings is factors such as stigma against marginalized populations and bias, which negatively impact patient care. A negative bias towards non-white patients was associated with their treatment practices, as well as worse patient outcomes. This was reflected when Black and African American patients received negative verbiage in their medical history. And this is not also just for one small population. This is also reflective towards obese or overweight populations, where doctors often tell their patients to lose weight as a treatment rather than actually caring towards specific needs. These factors lead to the next finding, which is that there is a negative overall bias, and poor reporting leads to errors in diagnosing patients. And it was found that there was a 23.5 to 28% error in diagnostic error rate amongst adults and children. These factors compounded to play a direct cause in the next finding, which is current requirements for gathering and collecting electronic health records, which often do not align with patient needs. Systems tend to be designed to meet administrative goals rather than focusing on patient care and satisfaction. In addition, the data gathered is not in the volume and frequency that's often required for these AI systems to function at their best. The best implementation of AI is currently overrepresented by clinical specialties which focus on high volume of imaging, such as radiology. Another factor is data sets which receive external validation to ensure accuracy, but foregoing internal validation due to lapses in assumptions. Models have high accuracy within the organization it's developed, but subsequently perform poor at other institutions within similar population groups.
Thank you. Thank you. I appreciate it. I just want to encourage others to contact us as we continue to work on this. We work at an HBCU, and it's especially important that disparities and bias that people are using in their AI tools in healthcare be taken care of. Thank you very much, Lisa.
Yes, thank you, Deborah and Chris and Amrit. And I'm going to check again. Here is Aswini here. No, okay. Indica?
Yes.
Okay, very good. I will pull up your poster here.
Indica is actually my professor. I'm presenting on behalf of him.
It's the correct one here for you?
Yes. Yeah.
Okay, great. Take it away.
Thank you. Hi, everyone. My name is Prajwal. I'm a graduate student at the University of North Florida. This is my research on explainable automated inconsistency detection in biomedical and health literature. Biomedical and health literature refers to the scientific knowledge published in the fields related to human health and disease. That could include research papers, journals, books, articles, etc. Every year, thousands of research articles get added to a health archive called PubMed. As you can see and the image on the left side of this poster, the bar graph, you can see that there is an exponential growth in the number of published articles on PubMed. While it is a good thing that every year new research findings gets added, but with the increase in the number of research findings also comes with a simple challenge, and that challenge is the increase in misinformation and contradictory findings as well. According to a research, 67.5 to 81.5% of American adults, they search health-related information on the internet, and at max, 30.3% of what you see on the internet is accurate regarding health, according to another research. So there's a lot of misinformation in the internet. Let me give you an example. Use of vitamin C for the treatment of COVID-19 was widely popular during the pandemic, but we couldn't find any research paper or a source that would claim that this is a true statement, an accurate statement. So this can be really challenging for clinicians and researchers who want to stay up to date with the scientific knowledge. And since health is a sensitive field, that's why this research started. So on the figure one is the complete pipeline that we have been working on. This basically includes two main components. The first is the information retrieval system, and the second is the machine learning classifier. The information retrieval system can take an input as simple as the effect as simple as coffee and health effects, or the effect of coffee on health, or many other queries. And what it does is it goes to different documents or research papers that are related to coffee and health effects, and collects sentences that can answer the effects of coffee on health. That's how we collect like a lot of sentences, and these sentences are further passed through a machine learning classifier, which is a fine-tuned BERT, large language model, that is able to tell whether there is a contradiction existing between those sentences or not. For example, if some sentences say that coffee is good for health if taken in this amount, and the other sentences say that coffee is like bad for health with certain conditions, there's definitely a contradiction existing between that, and that's what our machine learning classifier looks at and classifies whether those are contradicting with each other or not, and then labels the particular query or the topic as contradiction. And we also further explain the contradiction by giving proper sources from where those sentences came from, and why the machine learning classifier is classifying them as contradictory. On the information retrieval system side, we use retriever and the reader pipelines to look at the syntactic and the semantic similarity between the query and those documents and the sentences. And on the machine learning classifier side, we basically first work on pre-trained models. We fine-tune them on a man corpus dataset. As you can see on the reference one there, it's a manually extracted contradiction corpus developed by Alamri and Stevenson. We fine-tune our bot models on those, and then yeah, that's how the classifier is developed. And right now, PubMed BERT is our the finest classifier. And yeah, so we think that with the use of this pipeline, we'll be able to decrease misinformation and contradictory findings in the field of health. Yeah, thank you, everyone. Thank you for listening.
Thank you, Prajwal. Alan?
Hi, Lisa.
Oh, hey, Alan. Okay, I'm gonna bring up your screen. How are you doing?
Doing well. Thank you for doing all this.
Mhm. Okay.
Great. So while you're doing that, and I know folks have access to these posters as well outside of Zoom, just want to say hello to everyone. My name is Alan Flynn. I work at the University of Michigan in the Schools of Medicine and Information, and I'm a member of the Knowledge Systems Lab. This is a poster from our lab for MCBK North America 2024. And a couple of starting points to understand what we're talking about in this poster. From the previous work that we've done today together, answering some questions and sharing, our lab, we focus on what were referred to earlier as goal-oriented or task-oriented models. Some of those models arise from machine learning and AI methods, things like classifiers that were just mentioned, models for natural language processing, and a host of other things. We think about what it will take and what additional information needs to go along with these kind of machine learning models in order to make them findable, accessible, interoperable, and reusable, which are the FAIR principles that have been talked a lot about in a variety of scientific circles. Our group for a long time, we've pursued formal but flexible models of what we call knowledge objects. And a knowledge object is a digital object containing CBK artifacts or models alongside other relevant content. Metadata describing the model, tests that can come along with the model so people who receive it can test it and understand whether it's performing as intended, user documentation, end user licenses, and fitting into today's earlier conversation, perhaps also we could start including things like useful prompts for an LLM about our goal-oriented model, things like that. Then what this poster describes is essentially our work over the last year on what I'll call multiple ways problems. And the multiple ways problems that I'm referring to are that there are multiple ways to represent in programming languages various machine learning models and various other CBK artifacts. And so we're thinking of knowledge objects that could contain, and we've built some examples of these, the same or nearly identical algorithm or model represented in more than one way, so that individuals who are used to receiving their models programmed in one language or in using one set of methods could have those, but other individuals who are looking for something else could also have a different representation of the same or nearly the same thing, and receive that all in one package that we call a knowledge object. Similarly, another multiple ways problem that we've been working on has to do with deployment methods for these CBK artifacts. How do you actually run them, in other words? So in the past, we've shown and done demos at MCBK of putting alongside the CBK artifact enough information so that you can quickly stand up an API that allows for that artifact to be engaged and compute something. We're also looking at ways of including command line interfaces, web apps, smart apps, CDS hooks, and other deployment mechanisms that could go inside the knowledge object as an option in order to make it more useful for the people who receive it. And so this is what's described in this poster. Thank you for letting me present.
Thank you, Alan. So next is Siddharth.
Yeah, that's me.
Okay.
I have space for us to submit 5 slides instead. I do have those ready. Is it okay if I present and share screen from my end?
Sure, absolutely. That'll help me. I was going to say, then you'd have to tell me like next slide. So that's great. Go ahead.
Okay, perfect. So let's give that a go. Perfect. So I think you guys should be able to see it now.
We can.
Perfect. Okay, so nice to meet you guys. My name is Sid. I am a second-year medical student at Carleton College of Medicine. I have some background in math and bioinformatics, and that's really where I'm coming from today. What I was interested in is these two different representations of knowledge called knowledge graphs and causal models. And I just kind of wanted to build them out because what I found is that, especially in my own education, I found myself memorizing associations over and over again without really knowing why they were there. And I thought, like, hey, this would be an improvement to education, but also it's an interesting computable biomedical knowledge artifact. So in the interest of time, let's move on to the next one. This is just kind of some background about what they are. If we haven't encountered knowledge graphs and causal models already, knowledge graphs are kind of ways to store knowledge that include, nodes and then connections between the nodes or edges, right? You might store that A is associated with B, or that A and B are, they've got an antagonistic relationship, and that would all be within the same graph. Whereas with a causal model, the only thing you care about storing is that A causes B. Anything else doesn't really have a place here. And so kind of the upshot here is that, there are ups and downs to each approach, and it turns out they're not mutually exclusive. You can actually make something that is a combination of both. And so a brief aside to, kind of biochemistry, because it's a great proving grounds for everything. What I want to do here is really focus on the left side of the screen, points 2 and 3, where we've got this reaction going on, and we've got this enzyme B that's kind of modifying the reaction between A and C, right? And so just that's a reaction, that's kind of a situation that you can't represent so well in a graph database. Which is what, knowledge graphs and causal models both kind of use, path diagrams both use. And so effectively, what I've had to do is kind of build up a higher order graph, a hypergraph, in order to be able to represent this relationship. I'll skip kind of the details here in the interest of time, but kind of there are ways to preserve the causal inference that you can do on a causal graph so that you can continue doing them on this kind of new thing. So what I've made basically is a database here that has a custom type system that lets it infer from data. So if we look at the right top corner, we've got a small diagram there that's all the data in the database. On the left top, we're just doing a regular search in kind of a knowledge graph mode, where we're looking for all the inhibitors of phospholipase A2, and it found the right one, lipocortin. But now if we go down below that, we're looking at inferred knowledge. The model doesn't really know that lipocortin is kind of decreasing the concentrations of arachidonic acid or cyclic endoperoxide, but it's able to infer from all of the things we put together. It composed the two relationships we had, and is able to tell us that, we're expecting to see these two go down. So kind of the upshot of this is, imagine kind of in a clinical presentation, a patient comes in with a set of symptoms. Clinician is asking what are all of the diseases that can cause a set of symptoms. And so we start to look at, all possible causes. We do this backwards search. And then if we have information about, relative likelihoods, we can optimize that patient's workup by looking at the amount of relative information gained by each diagnostic. So that's kind of really the upshot here. A couple of challenges going forward, just UI, putting in data, but that's the situation. Anyways, if you guys want to check out the code, you're more than welcome to visit the QR code or the link at the bottom right, and I'm happy to take questions about Thank you.
Oh, thank you, Sid. Is Saket here?
Yeah, I'm here.
Okay, great. I can share my screen and okay.
Perfect. Hi, everyone. My name is Saket Bodapati. I'm a second-year undergraduate student at the University of Michigan, Ann Arbor, majoring in biopsych, cognition, neuroscience while pursuing a pre-medical track. And at the university, I had the opportunity to collaborate with Dr. He through the medical school and build upon the work done by Long Tran on the study. So the foundation of our study comes from the Observational Medical Outcomes Partnership Common Data Model, shortly known as OMOP-CDM, which is a standardized platform used to share and analyze observational data. And it integrates various different databases of clinical data and encompasses the health records of billions of people around the world, as shown in Figure 1. And so while this model is effective, there has been some shortcomings to it. Some parts of it lack clear meanings, making it hard to understand and use the data, especially when we're trying to recognize patterns at the higher level. And so in order to address these, we developed a solution called OMOP to OPMI, which is a subset of precision medicine that ontologizes all the elements and terms of the model, which couldn't be done by the OMOP CDM. And so ontology is just another way of saying semantically representing a domain. So for example, if we have a domain of medical conditions, the concepts would be the different types of conditions, such as diabetes, hypertension, allergies, and the properties would be the symptoms, the treatments, and the severity of the condition. And so with this information, you would create an ontology, which would be used by healthcare professionals to find associations between the condition, the symptoms, and treatments available. And so the OMOP to OPMI uses a similar strategy, and it's structured into a hierarchy, where we were able to add semantic relations, as shown in Figure 3, in order to understand the connections between terms. And the way we map terms follows a pattern, briefly shown in Figure 2, where the OMOP CDM term is searched in the OPMI database and then imported to our list. And the way in which I did it is described in Figures 4 to 6, where I would start by first finding a definition of the OMOP CDM term, so that I'm completely aware of the term I'm trying to map. And then I would search the term in the OPMI ontology. And then if I didn't find the right term, I would extend my search to all ontologies. And so before, 51% of the terms were mapped through this process by researcher Longtren, and now I was able to extend upon his work and map about 71%. And we need to continue this process and create the unmapped terms in the OPMI database so that we could finish the process and get closer to 100%. And so on the left, on the right, under case 1, the OMOP OPMI has the potential to map all CDM models, which will eventually lead to ultimate data standardization. In addition, while OMOP CDM was able to explain vaccine adverse events, this model would be able to define and model these events as well. And we also want to apply case 3 by using our model to model COVID-19 data from the National COVID database and explain kidney conditions such as acute kidney injury, chronic kidney disease following COVID-19 infection. And so overall, we hope to extend the practical use of our model we created and provide strong relationships between data, which will eventually lead to support various medical applications and advance our scientific understanding of medical conditions affecting people around the world. Thank you.
Thank you, Saket. I'm going to check one more time. Has Sweeney joined?
Yes, I am here.
Okay, very good. I'm going to pull up your presentation, and then after you are finished, we can.
I can present my screen if you'd like.
Yes, I have it here. So here we go.
I can share my screen if you'd like.
Oh, okay. Yeah. Do you have something other than this slide here?
Yeah, because
Okay.
it is easier for me to talk from here rather than.
Okay. I understand.
Are you able to see my screen?
Almost. It looks like it's starting. Yep.
Okay.
Yes, we can see. Mhm.
Okay. There is a little bit of internet issue, which is why I was a little delayed. But let me try my best. Hope we can reach till the end. So thank you for letting me present here. And I'm going to present here about a study that we conducted in the UK. The big question right now is what is trust? It's a question which perplexed 3 out of 5 individuals when they were asked these questions concerning AI as per a 2023 KPMG survey. To understand the chasm between the apprehension and innovation, we carried out a research project in liaison with all our research partners, innovation partners, involving 74 UK residents who were a part of academic health science network, public involvement CNET, and some patients were recruited from the patient groups on social media. We created a public resource page or a public resource web page where participants were able to interact with the medical chatbot. 2 days post interaction, the participants were asked a question whether they would like to go to the nearest when they go to the
Sweeney,
and we used the
we lost you there for a minute, just to let you know.
sorry.
You were cutting we lost you there for a minute. I just wanted to let you know. So, oh, I guess we lost him altogether. Okay. Well, why don't we move on to Q&A? So do folks have questions for the folks that presented?
So I'd like to ask a question. So we had the opportunity to hear from a couple of students, and I'd like to hear from either of them if they have had a chance. So this is obviously research that they're doing as part of their studies, but have they had an opportunity to apply this either in their training or in any kind of work environment yet?
Hi, yeah, thank you for the question. I'm happy to speak to a little bit of that. I think as far as this project goes, we're still far from really being at a place where we can apply it well. And so I think, again, a couple of those hurdles are putting in the data into the system to make it something that we can use for training or for practice. And two, we need to do some kind of validation studies to make sure that, it does help before, it becomes a bigger thing. And so both of those are going to be hurdles that we need to address before we can get there. But it is something we hope to do.
Wonderful, thank you. And I'm wondering, would anyone like to talk a little bit about next steps for their work or communities that you're interested in engaging in your efforts?
I have one next step question, Christy. Does the University of Michigan, and Kathleen might be able to answer too, do you have a good repository for putting OER information? I heard there was something called a blue box.
Oh, it's Deep Blue.
Say it again.
It's called, I'm sorry to speak out, it's just repositories are like my favorite topic. So, this is the right crowd to admit that. Yeah, it's called Deep Blue. It's the institutional repository based at the University of Michigan. I might also, just because, for instance, for our institutional repository, we do have some requirements as far as depositing and affiliation. So what I might suggest to you is to consider a generalist repository. You can deposit regardless of affiliation or your role or anything like that. And this is a great opportunity also to get it kind of out into the broader world. I'm going to put I need to find a couple of links and put them in the chat, but there's an initiative being sponsored by the National Institutes of Health called the Generalist Repository Ecosystem Initiative. And you have a lot of these kind of like larger repositories that are kind of a welcoming home for everybody and any topic for deposits. And so just full disclosure, I work on the Zenodo project that's based at CERN, and we've been contributing to their open source project for a while. But just speaking on behalf of that repository that's part of GRAY, this generalist repository group, you can create communities, and then you could have all of these knowledge objects in a single place that can be, you can search within that space. So I'll grab those.
And I can email you afterwards, and thank you, Josh, and others that have given me comments, Alan. What we want to do is to make sure those that are knowledge managers and librarians, both here and in the UK, that I work with, that they have a chance to understand how to build a repository with all this wonderful research information and the knowledge objects that were described by others. Our work came from Dr. Friedman being the first speaker, from Rachel Richardson and others. So we have a deep blue connection. But thank you, Christy. I'll email you later. And I believe in open education resources. And I thank Jerry Perry for connecting me to that too with folks in Arizona. It's important. It's changing the world. Less textbooks.
Yes.
Thank you. Thank you.
Okay, other questions, comments?
Lisa, I was just going to respond to Christie's and others, note about potential next steps. So one of the things that our group, the Knowledge Systems Lab, is thinking a lot about these days is combining a variety of different CBK artifacts or models into knowledge bases. And so it's one thing to have knowledge objects that encapsulate and describe individual models, but it's another thing to pull a number of those artifacts together to support an application. And so we've become very interested also in the idea of constructing knowledge bases from atomic digital objects or knowledge objects. And so that's an area of future research for us.
That's great. I mean, it's such an interesting space. And I think, kind of as indicated by these, this conversation is sometimes it's the very practical things of how do you make things available? How do you make them discoverable? How do you make sure that you're connecting with the right audience when we are in such a distributed and virtual everyday work environment? So that sounds amazing. Thank you.
And I think from Philip Scott's comments earlier today, from the UK perspective, just echoing those, the quotient of rework here, it can be very high. And so until we can share some of these effective models, goal-oriented kinds of CBK artifacts, we're going to continue to see folks who are trying to solve the same or very similar problems in their own space, in their own way, and not achieve some of our goals here in terms of the power and effectiveness of CBK. So I'm all for sharing and really appreciate the discussion here today around these posters along those lines.
Yep, definitely. Definitely. I did put in just for perspective, there's a blog from the Office of Data Science Strategy Director, which is the first blog, and then just a recent poster with random information. And then outputs. But I mean, to your point, it's really important to get these things discoverable. And that's where all of our friends who are working in this space and working on data standards for discoverability can really make magic happen. So this is wonderful. Thank you, everyone who presented, and we'll be looking forward to the ongoing discussion.
Yes, thank you.